So, we now get into the mainstream of the course. Yesterday I had introduced you to the subject of iron and steel making, given you an overview, and now today onwards we are going to enter into the main contents of this course. And for the next 17 lectures, as I have mentioned, we will 16 lectures or so we will be spending time on iron making. And for the next 5 lectures we will be mostly talking about a blast furnace iron making. So, starting today, next 5 days we will be talking on blast furnace iron making, mostly talking about the furnace itself, the equipments, the sensors, the thermochemical processes inside the blast furnace, what are the modern developments, and so on, so forth. I will try to give you a nice overview, emphasizing mostly on the scientific part of it and not dwelling too much on the features, the construction, the description, etc., and try to make it interesting so that you can understand the complexities of the process, the beauty of the process, and see how such a huge structure or a reactor can produce or churn out an enormous amount of liquid hot metal on a daily basis. Now, one more information before I start the lecture. I would like to tell you that in this course I will be following these 2 textbooks which you can see here. These are perhaps for undergraduate education the best 2 textbooks available in the market. Okay, so this one is written by me, and this one is written by Dr. Amit Chatterjee and Professor A. Ghosh, who was also teaching at IIT Kanpur. So, I would advise you to procure either of these 2 books and do a more comprehensive reading than I could cover in this particular course. Now, with these words, let me get into the subject and today's topic. So, mostly today the construction of the furnace, we will try to design an operation, that is what we are going to do, and we will also study the blast furnace. That the furnace alone does not operate, it operates with many paraphernalia, and we will see that what are the essential components of or accessories of blast furnace. These are by and large the 2 main topics of today's discussion. Now, let me start by drawing a schematic of a blast furnace. So, that is how the blast furnace looks like, and precisely we can, this is a huge foundation on which the structure rests, and this is just one part. So, I will draw here a central line, and that is how the central line, those of you who are not well conversant with engineering drawing, okay. So, that is how the central line is drawn. So, the same half is there, it's a symmetrical structure about this central line, and let me thicken it a little bit to give you an impression that the structure is not so thin, okay, as it looks like, and it is actually a refractory lined vessel, and that's. And I would also like to make one more interesting observation here to show you that, look, this furnace actually I have drawn it pink all through. So, I will just try to demarcate that maybe here it is not pink, here it is blue, and here it is, just to give you an indication that, look, the lining is not same as everywhere. Okay. So, somewhere the lining is yellow colored, somewhere it is pink colored, somewhere it is. So, different requirements are there, and that is why I have drawn it differently. So, this looks like the structure of a modern day blast furnace, and as I would have said yesterday that this height for a large blast furnace, and large blast furnace when we are talking about I am meaning 3000 meter cube, 4000 meter cube blast furnaces, and I would say that large blast furnaces could be about 2 to 3000 meter cube blast furnace. Giant blast furnaces could be about 4000, 5000 meter cube. That means the internal volume, we will study these things in greater detail later on, and this height could be on an average 30, 35 meters. And if you take the hearth diameter, these names we will introduce later on, and there you will see that we have something like 12 into 2, so it's about 20 to 30 meters in diameter. That's the hearth diameter, and here the diameter could be even bigger. Okay, so that is, so it's a refractory line, tall structure, and this is basically a shaft furnace. When you have a tall column, and this shaft furnace operates on counter current principle. That means the feed material is introduced from the top, and we have a gaseous material, gas which ascends, and this gas, so we put in here is air. Since the charge, it contains iron ore, limestone, these are all higher secondary knowledges, and you all know that, coke, and we will add that this is the naturally occurring material, iron ore, but we have an engineered raw material or iron bearing material, and those we call as sinters and pellets, which are now integral component, and these are, as I said, engineered iron bearing material pellets. So, these are introduced from the top, and these are introduced at the top at 298 Kelvin, which is at room temperature. So, this air which is hot is introduced into the blast furnace at about 1200 degree centigrade, or I would say 1200 Kelvin, isn't it? Somewhere it is, these are not, I mean, plus minus values are there, okay, because of the fact that all blast furnaces do not operate. We will see the value, we will see the significance of the number 1200 when we talk about the enthalpy input to the blast furnace in the next section, or in the next, during the next week. So, air maybe about 1000 degrees, somewhere around 900 degrees, depends on how the air is heated. We will see there are different mechanisms of air heating for different furnaces. So, I would say 4000 to 5000 meter cube. If this is the internal volume, then we will label the blast furnace as a giant blast furnace. Typically 2000, 3000 meter cube are modern day blast furnaces, most of the blast furnaces. Nobody makes it smaller. Larger blast furnace are better than a cluster of smaller blast furnaces. So, people, but there are problems we will see later on. These are modern day blast furnace. And then we have mini blast furnaces also in small steel plants, where the internal volume of the furnace is something about less than 1000 meter cube or so. So, the feed material, when you introduce hot air, the coke or the carbonaceous material, it burns with the combust with air, and as a result of which carbon monoxide is produced. And here the temperature goes to as much as in this combustion zone 1900 degrees centigrade to about 2000 degrees centigrade. That is a peak temperature, and there is a raceway which is created. The air, hot air gets into the furnace, it combusts and it creates some sort of a void in front of it, that the rate at which the coke is advancing into this raceway is exactly equal to the rate at steady state to the combustion rate, and as a result of which a raceway region is established right in front of the two air. We will draw a sectional view of this furnace a little later. So, this is called raceway. So, please note down the terminologies that we and this through which air is introduced, hot air is introduced, and that air, hot air is introduced through what is known as two air. And so, the carbon monoxide which is produced here, and how do you know it is carbon monoxide, not carbon dioxide? We go back to Ellingham diagram and we see that at such a high temperature 1900 degrees centigrade, carbon dioxide is not a stable phase, it is carbon monoxide, and when we have enormous amount of coke which is available within the blast furnace, it is only carbon monoxide. So, the carbon monoxide and the gas is introduced because the gas or the air has to cover this much of resistance, and the gas, product gas or the off gas which will go out of the furnace, and this off gas we will see what it is. This off gas is not going to be at this temperature, this off gas is going to be at significantly higher temperature, could be about, you add 300 degrees more, so 598 degree or 550 degree centigrade or 550 Kelvin or so. So, therefore, we can say that the descending column of iron bearing material and the ascending column of the gas, as they travel within the furnace in an opposite direction, and that is why the name of the reactor is it works on the principle of a counter current principle. So, the descending column of iron bearing material and the ascending column of reducing gas, which is carbon monoxide, they meet, and as a result what happens is the exchange of raw materials or the ingredients take place. Carbon monoxide, because the temperature from 1900 degree will decrease, and as a result of which what happens, stability of carbon monoxide will increase. As it rises up, it will have a more tendency to get oxygen, and where from it will get oxygen, but from iron ore, where oxygen is relatively loosely bound rather than from limestone. So, as a result of which iron ore, so it gets reduced. So, the iron ore which descends as a solid particle within the furnace, and the carbon monoxide which ascends within the furnace, they react with each other. Somewhere they are going to meet, and the net result is the production of solid iron and carbon monoxide, which goes down. Of course, because the charge is moving, we are continuously taking out. I have not completed the drawing, and I will draw the complete it soon. So, since we inject air here, it is understood nitrogen is inert. So, the off gas will contain nitrogen. The off gas will contain carbon dioxide, which is the resultant of the oxides, and the off gas will also contain carbon monoxide, because complete conversion is not thermodynamically possible, or I would say kinetically not possible. It is not thermodynamically, it is kinetically not possible. Okay? On top of this, there could be other minor materials, but most interestingly, because the gas is injected at a very high pressure, okay, it has to ascend through a height of 20-25 meters, where you have packed with all solid materials and some semi-solid materials. So, large pressure has to be applied when you inject the gas through the tuyeres, several atmosphere pressure, and as a result of which what happens, lot of solid materials are worn out, and this contains a significant amount of dust, and this dust basically is some iron ore powder, some limestone powder, some coke powder, everything I have bought with money. So, the dust is a valuable part of the output. We cannot throw it out. We must understand it is a very rich material, and it has to be somehow agglomerated and put back into the iron making circuitry in order to have the better economics of the process. So, the iron gets reduced, oxygen, carbon monoxide gets oxidized, and as a result of which iron is produced. So, that is roughly the principle of the counter current reactor, and we will understand that in this journey what happens is the pressure, the contact time is very important, that the gas particle as it descends, the solid particle as it descends, it is going to be surrounded by various kinds of gases. So, what is the contact time of carbon monoxide with the solid particle is very, very important. Also, it is important that what is the characteristics of this solid, that whether the gas, the gas has to not only react at the surface will be soon iron. So, the iron ore will be sitting somewhere inside. So, the gas has to go inside and then catch this iron oxide and reduce it. So, the characteristics of the ore, the contact time, etc., are very important parameters as far as the efficiency of chemical reaction in the blast furnace or iron production in the blast furnace. We will draw a line here which we will call as a stock line. So, this is laser monitored mostly. So, how it descends, it will go down because carbon is getting combusted, and as a result of which carbon is converted into gaseous product, what happens, this descends, and this determines that at what rate you should be charging into the feed through the top. Now, at the bottom, at the heart in the furnace, we have two, I will draw them as a little bit tapered. Okay. So, these are slag and metal notch, and we have roughly about 10 degrees. These notches are not straightforward, not here. So, I would draw an equivalent. So, this is my hearth. So, this is, if I expand, this is my, and this has, if I do it like this, then this becomes my, roughly, yes, that is the complete shape of the blast furnace. Okay? Now, you have a true picture of the blast furnace. So, we can have the metal, the slag, this is called the slag notch. Slag is produced from the impurities, mostly contains oxides, which are very stable oxides, and at even 1900 degrees centigrade with pure carbon present will never get reduced. So, those gangue materials or oxide materials which are unwarranted present in iron ore, mostly alumina, mostly silica, this together with the gangue material presents in coke and limestone, they all accumulate and they become what is known as the slag layer. Okay? And then below it we have the metal layer. Metal is heavier, so the iron in the liquid state. And yesterday I have made, because the blast made that statement that primitive man could not produce liquid iron because they could not create a temperature which is as high as this, because we require more than 1500 degrees centigrade to produce iron in liquid state. And we must understand this iron is not pure iron, this iron is going to be alloyed with, most importantly, carbon, because carbon is abundant in the furnace, and we will see how it gets alloyed, and carbon is abundant in the furnace, and carbon has great solubility in liquid iron. We understand that we will cover all these things in relatively more detail, because I want to introduce the subject quickly. We must understand if this material is rich in carbon. So, therefore, if you have a carbonaceous material as lining material, possibly this lining material will not dissolve in the hot metal, because there is no potential difference, or the activity of carbon in the carbonaceous refractory and activity of carbon in the hot metal are going to be identical. Both are going saturated phase, this is saturated, so activity is equal to 1, activity is equal to 1, and therefore, lining of the hearth is always done, particularly the lower part of the lining or the hearth and the base are always done with carbonaceous material, which does not dissolve, giving a prolonged refractory life to the bottom. On the other hand, these refractory linings are of different categories. For example, the refractory lining here is going to have the capability to withstand very high temperature. On the other hand, here the solid material descends, so the abrasive resistance of the refractories are going to be, and that is why I have drawn different colors, just to give you an idea that the requirements of refractory in different parts of the furnace is different. And then we have this metal notch through which the metal is periodically taken out. This is a fascinating area of the blast furnace, that you have this big diameter, and the molten metal when it is opened. So, how it is closed and how it is opened is an engineering marvel really, because you have such a high ferrostatic pressure in the furnace. So, gunning, refractory material in slurry and paste form are introduced to keep it closed completely, and then we have this actually looks like, if you draw the refractory, then this will look like something like this. The refractory is very thick here, so this is the way it looks like. And this passage is going to be sealed, okay, otherwise all the time material will go out. That is the batch process, so we will take out material periodically. So, when liquid metal has been drawn out to a significant level, its level is gone down, in that case by using refractory paste, what happens is this particular passage or the slag notch or metal notch is going to be closed, and then when the time will come, okay, which is known from the processing conditions, a drilling machine will be put in to drill the material and to open the passage so that molten metal can flow out. The temperature here, as I said, maybe 500 degrees centigrade at the stock line, and then 1900 degrees, the largest region. The temperature here goes down a little bit smaller than the temperature here, because heat will be, mostly there is a huge convection currents. So, even though the radiation will take place in all directions, but the convection will try to predominantly take the heat. So, the heat tends to flow in this direction, leaving the metal and the slag at somewhat smaller temperature than 1900 degrees centigrade or 2000 degrees centigrade, which is the peak temperature of that. This part of the furnace is called the stack of the furnace or the shaft of the furnace. So, we can call this as upper stack and we can call this as lower stack. This is wash or the belly, and this is the hearth of the furnace. These are the, if you look at the cross section here, so if I say this is AA, and if you look at the cross section here, it is interesting how the air supply arrangement is, that is what I want to show. So, if I take a horizontal plane and let it pass through this particular AA section, then from the top what we are going to see? We are going to see that this is the blast furnace, and there is a pipe around the blast furnace which we call as a bustle pipe. This bustle pipe is connected to an air supplier. So, compressors, huge compressors, and there are a lot of things downstream here. So, the hot air comes here, and this bustle pipe distributes the air inside around the blast furnace periphery, around the Bosch region, and from this we have lot of, these are now my tuyers. That is the design. So, it is like a wheel sort of a structure. This is the way it is. So, there are several such tuyers, number of tuyers connecting the bustle pipe and delivering the air inside the blast furnace. Okay? And you can imagine that the blast will never be able to penetrate to this diameter, if this is 30 meters, and you have such a huge resistance in the path of the gas. You can imagine that what should be the force of the compressor in order to drive the air right up to the center core of. So, there will be a region within the blast furnace where the injected air is not going to be reaching, and around each of them there is going to be this. These are what? Many raceways, and there are windows in blast furnace through which you can see these raceways actually. That is what is the scenario that will look like. So, in front, and here the combustion is taking place. This part there is virtually no combustion taking place, because it is already carbon monoxide, and what is here? We will see that all the materials charged into the blast furnace except coke becomes liquid at this particular temperature. The slags, which is a combination of various oxides, acidic oxides and basic oxides, will be liquid. Iron will be liquid at this temperature, but coke is going to be solid through and through. Okay? Carbon does not melt at 2000 degrees centigrade. So, this part what is drawn here is basically superheated coke, which is sort of this coke is here, and it looks like something like this. This is the coke bed. That is what is the sectional view if you look at from the top. So, you will see that this part is what is shown as the region where coke is there, and which is possibly undisturbed by the injected gas itself, because the gas is simply not able to penetrate up to that the central region. And this coke is basically very light. Okay? It is much lighter than slag, it is much lighter than metal. So, it floats, and as the slag level, metal level goes down, this layer also goes down. So, it makes this kind of a movement within the blast furnace, depending on whether it is in the emptying phase or tapping phase, or whether it is in a non-tapping phase. So, therefore, this part of the coke is unreacted, and we will see later on this coke gives rise to what is known as a dead man's zone, because there is no activity there. Carbon monoxide will never react with this coke, okay? Cannot react. Carbon dioxide can only get oxidized to carbon dioxide, react with oxygen. So, therefore, once the carbon oxidizes carbon monoxide, it ascends because of its, there is a huge pressure difference between here and here. It is close to 1 atmosphere or 1.5 atmosphere. On the other hand, this could be about 10 atmosphere here. Okay? So, this drives the flow in the upward direction, and all the gas moves. So, there is another important part on the top that we have. The top construction is too complex to be drawn on the board. So, I would like you to look through an internet or look into my book, which has a one copied figure from literature, which illustrates that what is the complexity of kind of complexity that is there in the top part. We must understand that we cannot discharge the hot gas into the environment because of environmental regulations. So, it contains poisonous gases like carbon monoxide, it contains enormous amount of dust, and if you look at a modern blast furnaces, how much of dust is produced? We will do a calculation later on. It is about 200 metric tons of dust a day. That is the count of dust which flows out along with. So, the gas, as you can see, contains dust which is a valuable material, 200 tons per day. It contains, its temperature is what I said, it is about more than 300 degrees more than the charging temperature. So, it could be about 350 degrees centigrade, and what I have also, the composition tells us that it has a sensible heat because it has a high temperature exit temperature from the furnace. It has a chemical heat because it contains carbon monoxide which can be further combusted to produce carbon dioxide and heat. So, therefore, the off gas is a very valuable material for us as far as iron making. The effective utilization of heat and material and the off gas to a large extent determines the efficiency of modern day blast furnace operation, quote unquote, and this you must remember. Okay. So, this drawing is too complex, but it has, I will just mention, I will not try to draw it because it will take too much of a time. I suggest that you just give a search word in internet when you go back and look at blast furnace top, and you will see various kinds of designs. Okay. It started with a cup and cone arrangements. Anyway, the major objective here is that we will not be able to, we have to charge material inside the furnace periodically, and yet we cannot allow the material to go out of the furnace. This is the foremost requirement, that we will use the top to charge all the feed materials, but at the same time we will not let a single molecule of this poisonous dust laden gas to go out of the atmosphere. On top of that, there are various other, because all requirements, because all the materials here do not have the same size ranges, as we will see later on when you talk about the burden material distribution, and all the materials also do not have the same density. So, if you just dump them as it is, they tends to segregate. So, we want to design a system at the top which can also distribute the material very evenly, across the cross section. Why the distribution is so important? Because the gas is moving up. If the gas finds the path of least resistance, I want to give equal resistance to the gas as it ascends to the blast furnace, and that is only possible provided the cross sectional average bed porosity at different heights become identical. Okay? And that can be ensured by a judicious distribution of material around, right from the stock line itself. And so, therefore, the top charging arrangements has to also facilitate that it has not only to charge material into the furnace, it has to not only prevent the hot dust laden gas to go out, but it has to make sure that the materials as per their density and size are properly distributed within the furnace, such that we can ensure a good bed, uniform bed permeability. The word permeability is used to determine that you have solid particles here, okay, when you charge, and these solid particles touch each other, creating some kind of an empty space in between the solid particles and through which the gas flows actually, and that is referred to as permeability. So, more uniform the permeability of the bed is, and the function, some blast furnaces are very efficient, some blast furnaces are not, and it is because of all these kinds of paraphernalia that whether the bed permeability is same or not, what is the size distribution which is according to the requirements of operation and so on and so forth. So, you may not, if you just ensure that you are charging particle and you are not allowing gases to go out, that is in today's context is not enough. Also, you can see that iron ore which many people charges into the blast furnace, or when we were students, predominantly blast furnaces used to be fed by iron ore, but today mostly blast furnaces are fed by sinters and pellets, because these are engineered materials, and they have tailor-made strength, tailor-made porosities which perform much better than the dense iron ore itself. So, we must also understand when you prepare these engineering materials, and as the material is 30-35 meters height, you can imagine if you have a solid particle here, how much of a load, burden load is acting on it. So, and if the particle crashes, okay, then what happens is the high flowing gas flowing at a high rate, at a high pressure, will just take all those things along with the off gas out. So, we cannot charge fine particles inside the blast furnace, they will be all taken, illustrated away. Okay? So, therefore, there has to be a certain size ranges which for a given gas flow rate or the required gas flow rate will not be illustrated from the furnace itself. We do not want fluidization also in that. These terminologies all you have done when you have studied at the second year level rate processes. So, most of the fundamentals that we will talk about you have actually studied in the second year level of engineering when you have done rate process course or a transport phenomena course or an equivalent laboratory at the end of second year or the beginning of your third year courses. So, therefore, we have to charge them in lump shape, but if you have a very dense particle then the carbon monoxide gas will not penetrate, reducibility will not be high. So, we have to ensure that these engineering materials not only have good reducibility, good porosity, but also should have good strength such that they do not crumble under load into minute particles to be elucidated from the furnace, defeating the purpose of iron making altogether. Now, this blast furnace, so we will discuss further about this blast furnace. We will move internally, see how the temperature of the gas varies, what are the reactions in different parts, those we are going to talk a little bit later. But as of now, it is clear that I have given you a very sketchy overview to initiate the discussion on blast furnace iron making. You have a good idea about the reactor, the principal reaction in the reactor, and I would say if you say the two principal reactions in the blast furnace, from a very elementary stage, and you say that this is these two reactions. This is in the raceway which produces heat in the furnace, and this so the carbon serves as fuel if this reaction produces heat, and carbon produces the reacting gas or the reducing gas which reduces iron oxide. Carbon has a very strong function, and this carbon we introduced into the furnace not as coal but as coke, because coal will not be able to withstand, coal has more impurity, and coal will also be not able to withstand the burden load, it will crumble into pieces. So, that is why, and from certain grade of coal only we prepare coke. Coke is again an engineered material, and for giant blast furnaces we do require coke where coal cannot be used because of operational limitations. So, the coke has two important purposes as we see here. It has more purposes that we are going to discuss later on, but as I have indicated that these are the two principal reactions. So, the counter current reactor, reducing gas is generated at the bottom of the furnace near the belly or the wash, the reducing gas goes up, and the combustion reaction which takes place inside near the tuer, that supplies the necessary heat. So, blast furnace operates on the basis of supplying of external heats, and that external heat could be, if we use for example hydrogen at high temperature, hydrogen can also reduce iron ore. Hydrogen has great affinity towards oxygen, but in that case what happens is you have to find out an alternative energy supply, because that reaction is not as exothermic, here the heat is produced, here also some amount of heat is produced. So, the combustion reaction is going to be altogether absent. There is no counterpart of this combustion reaction when you introduce hydrogen into the system. So, you will require either an electrical energy or solar energy to be supplied into a hydrogen blast furnace. But we will see that we can blend little bit of hydrogen through the tuer into the system, and we will see why that can increase the reduction efficiency in the furnace. But if you try to inject too much of hydrogen inside the blast furnace, then what happens is the blast furnace becomes cold, thanda, and then the entire reaction or the system of iron making collapses in the furnace. Now, this furnace, so we have seen that it requires a lot of feed material, so that we have to have ready stock of feed material. As I said, if this is 4000 meter cube blast furnace, it is producing 13,000 tons of hot metal. So, this hearth, what is this is slag as I say, and this is metal, and this metal basically is iron, carbon, silicon, manganese, sulfur and phosphorus. On the other hand, this slag is basically CaO, SiO2, principal constituents we will study in greater detail later on. About 4%, as I said, so lot of alloying additions or impurity elements are there. Roughly it is about 95% iron and remaining are 4% carbon, and remaining are 1%, 1.2% silicon, manganese, sulfur, phosphorus, and so on and so forth. So we have to handle. So this carbon comes from the coke. SiO2 and Al2O3 are impurities which are present in the iron ore itself. Calcium oxide comes from limestone. Sulfur, phosphorus, which are present. When you combust coke, then the residue left behind, the coke ash contains silica, sulfur, etc. So this sulfur, silica is also a part of it comes from coke. So these are roughly very basic elementary level composition. We will or constituents which makes slag and metal. We will see that how does the composition changes along with the processing of iron inside the blast furnace or the blast furnace operating practices a little later, which you need to develop enough understanding of the subject. So we have to handle a huge amount of raw material on a daily basis. We have to handle a huge amount of liquid material. Slag is in the liquid state, metal is in the liquid state. And as I said yesterday, that this is an intermediate product. This is to be taken for further refining. We want to produce steel, and as you all know, steel does not contain much carbon. And yesterday I have mentioned that this hot metal, which we call as pig iron, or if it is in liquid state, we call it as hot metal, blast furnace hot metal. This blast furnace hot metal, if you solidify, you get cast iron or you get pig iron, and that doesn't have much good engineering properties. It is brittle material, doesn't have much toughness, so that is not good for us to be employed in engineering applications. On the other hand, if you can control carbon, silicon, manganese, etc., eliminate a good part of it, then we produce nearly pure iron with less than 0.1% other alloying elisions or other impurity elements, and then it becomes steel, and then we get the required strength and so on. So subsequent refining of this is necessary. So this 13,000 tons it is producing on a daily, if you do it 6 times a day, every 4 hours, that means 200 tons you have to transport to the steel making shed. So you have to have good arrangements for transportation of the liquid. Also, as you can see that we have hot blast which is supplied. So the air has to be, there has to be arrangement for heating of the air, and there has to have huge compressors and compressor houses attached to a blast furnace, which will also be necessary in order to continuously supply preheated air into the blast furnace. Also, we have huge off gas. These off gases, as I said, it contains carbon monoxide, chemical heat. Carbon monoxide combusts to carbon dioxide, releases heat, and it contains sensible heat, but it contains dust. We cannot extract the heat until and unless we get rid of the dust. So cleaning of the blast furnace gas is very, very important. So a blast furnace is also going to be equipped with a very efficient dedusting system or dust GCP, which we call as a GCP, gas cleaning plant. So if you look at a blast furnace is going to be surrounded by a stockyard from which material will come. Blast furnace will be connected with pit house paraphernalia like those vessels and all which will transport liquid metals. Blast furnaces is going to be connected with a huge gas cleaning plant around it, and blast furnace is also going to be connected with air preheater as well as the compressor house, etc. And on top of that, a blast furnace has lot of paraphernalia attached to it in order to monitor the flow rate of oxygen, in order to monitor the level of the liquid, in order to see that what are the temperatures in different region, in order to see what is the refractory wear. So there is a blast furnace shop adjoined to the blast furnace, which is monitoring everything, which is overlooking the activity, that at what time charge is to be inserted into the blast furnace, at what time this is to be opened. So there are algorithms, there are sensors, there are computers in that room, and that really controls. You may not see 1, 2 or 10 people round the clock around the blast furnace. There has to be a control room, and from that control room we typically tend to control all this paraphernalia, transportation of vessels to transport the liquid, charging of the feed materials, cleaning of the gas, and controlling of the gas flow rate, how much of air is to be at what temperature is to be supplied, and so on and so forth. So there are various paraphernalia around the blast furnace. As such, this tall reactor is not enough. So you can draw an earth. Blast furnace is like an earth, and it is surrounded by several satellites, and those satellites, as I have mentioned, one is here for this, The other is for slag disposal and treatment. Slag is also, you have to solidify it, it contains lot of heat, it is at 1450 degrees centigrade. And if you just quench it, what happens to that slag? It is 30%. If you, as I have indicated, if you have 13,000 tons, so about 4,000 tons a day you are producing slag at 1450 degrees centigrade. I mean, if you just quench it with water before disposal, all that heat you have just thrown down the drain. So, people are trying to not to recover heat from, generate steam or recover heat from the hot blast furnace slag, they are also trying to recycle this blast furnace slag. This is an important modern developments in the blast furnace iron making technology. Okay? And we will see this, how this material, slag material can be effectively recirculated via various other processes yielding different engineering materials. So, we will just briefly talk about, let us look at this satellite, which is the supply of the preheating preheated gas, and these are called blast furnace stoves. These blast furnace stoves basically are, there could be 1, 2 or 3 stoves per furnace, because the blast furnace stoves are tall dome shaped structure. You cannot miss it. It is possibly as tall as the blast furnace itself, and we will understand why it is so tall. This has 2 different compartments. One compartment, again the drawing is there in all textbooks, or you can find it in nets. It has a brake checker work here. Through this, it is the bottom. So, you introduce air, which is air at room temperature, and then you use a part of the clean blast furnace gas, CBF, which I call as a clean blast furnace gas. If the blast furnace gas could be combusted here, okay, then what happens is that we can generate heat, and if the hot air flows through this to exit, this is not blast, okay, this is just simply air, we are combusting it. You can use oxygen also, okay, oxygen enriched air. And so, our objective is to first generate heat by combusting carbon monoxide, then tap the heat and then use that heat to heat the blast and then supply, as a result of which this carbon monoxide has been produced by burning coke within the blast furnace, and coke is substantially more expensive than coal. So, by recycling the chemical heat contained in carbon monoxide, we in turn have been able to supply back the coke that we have charged into a part of the reflex, a part of the coke that we have supplied into the furnace itself. I mean, if we use this carbon monoxide, okay, to combust and run, for example, light the electricity or the fan in this room, it is not efficient usage, but this supply of this heat back into the furnace via the stoves is a very important step in the iron making. So, this is going to be operated for, these are brick checker brickworks. These are like highly porous ceramic bricks whose bulk density is, they are light bricks because you have to buy less amount, and they are porous because they have surface area, and heat transfer, we all know that the hot gas which is going out after combustion through this will yield its heat to the brick, and that yielding of heat is directly proportional to the exposed surface area that we know from our fundamentals of heat transfer. Okay? And as a result of which, what is going to happen? After some time, this is going to attain a steady state where maximum possible temperature, which could be the combusted gas temperature. If you can create 1200 degree, 1300 degrees centigrade, then the same temperature can be created. So, progressively the brick temperature will go and attain its maximum value depending on what kind of a temperature we have generated. So, after operating about 2-3 hours, then what happens? This is closed now. So, the stove is now hot, and at that point the direction is reversed. Now, the cold blast is introduced, and the cold blast travels in a reverse direction, and the cold blast comes here and is injected through the air into the blast furnace itself. So, the phase in which combustion takes place within the blast furnace, we call it is on gas, the stove is on gas, and when we reverse the connection and the cold blast is heated, and then we say it is on blast. So, a stove is going to be operated in a cyclic mode, on gas and on blast, and we must understand that If you have only one stove, it is not going to suffice. You require at least two stoves, because when one of the stoves is going to be on gas, the other will be on blast, and that is how we can continuously supply hot air or hot blast within the blast furnace itself. Okay? And we must understand why do you want to make it taller, because we want to make the residence time larger. Okay? So, the gas is flowing in vertically downward through here, and we want that the gas solid contact is going to be significantly larger, and that can be only ensured provided the stove is very tall, and that is what I said, that the stoves could be as large or as tall as the blast furnace itself. So, you cannot miss it. If you go to a blast furnace and you look around and you will see there are 3 or 2 dome shaped structures adjacent to the copper stove, from which big pipe comes out and enters into connects the bustle pipe itself. You just cannot miss it. Okay? And then we have the gas cleaning plant, and the gas cleaning plant basically we have dust catcher, then we have Venturi scrubber, and then we have electrostatic precipitator, ESP, electrostatic precipitator. So, you have huge uptakes here, huge pipes coming out from the top, and that is carrying the carbon monoxide, carbon dioxide, nitrogen and dust, and where it is coming? It is coming to the dust catcher. So, this is how it looks like. So, this is from the blast furnace, and then it enters into what is something like this. That is the dust catcher itself. Okay. So, this is dust catcher. Again, the drawings are there in the textbook. So, I am not going to and then from the dust catcher it goes like this, and here what happens is the gas enters the venturi, okay, and there is the engineering component in the whole thing, okay, and then you have the scrubber here. So, water is sprayed and the gas goes out through maybe, and then it goes to electrostatic precipitator if this is needed, where you have the gas flows into the chamber, and you have a positively charged and negatively charged particles in the plates, through which when the gas flows, then what happens is because of attractive forces further particles are gets removed. So, 70 to 90% of the dust is going to be removed in the dust catcher itself. The dust catcher works on a very nice principle, as you can see, the gas is going to come here and it is going to reverse its direction, because I have located, I think 2 years or 3 years back there was a question of this kind in a gate examination. So, it reverses and to go out of the system, and during the reversal what happens is the solid particles, they go through a zero velocity, and because of gravity these solid particles try to settle down at the bottom, and which is periodically going to be removed. Okay. Now, up to this point it is dry dedusting, and then comes it is a wet dedusting, and remaining again here 70 to 90% of remaining dust is eliminated. So, the gas which goes out, blast furnace gas which goes out from the Venturi scrubber is almost clean. It does not contain much suspended particles, but you must understand that if you use a Venturi scrubber in the gas cleaning plant, then what happens is you have lost all your sensible heat. So, to recover the sensible heat which is present in the blast furnace, because the blast furnace gas does not go out at room temperature, we have today efficient dry dedusting system, where we do not use the Venturi scrubber, and the clean gas is at a higher temperature 200 degree 250 degree centigrade, and we will be able to recover that heat itself. So, here again as the gas moves up, water is sprayed over it. So, when water is sprayed, the gas part the dust particle, they absorbs moisture, and as a result of which their density increases, and as a result of which they settle. So, these arrows basically shows that periodically you are taking out the slurries and the solid particles which settle at the bottom, and these solid particles, as I have indicated, are very valuable materials, and they are going to be agglomerated, because as such these fine materials cannot be put inside the blast furnace. So, we will have to agglomerate and then use it, either in an electric arc furnace or within the blast furnace itself. So, we will continue with the discussion.